Okay, so let's continue our discussion of Hilbert spaces and orthonormal families in Hilbert spaces. Our initial data are as follows. We assume that H is a Hilbert space, well, just an inner product space. And suppose that EI is an orthonormal family in H. So let's recall that orthonormal means that it is orthogonal, that is, the vectors EI are pairwise orthogonal to each other, and also the norm of each EI is 1. And let's also assume that our family is at most countable. AMC for short. This is quite natural because we are mostly interested in separable Hilbert spaces because they form the most important class of such spaces. And we have proved at the previous lecture that if H is separable, then each orthonormal family in H is at most countable. So this is a very natural assumption. And also, so since this family is at most countable, we may assume that I is either the set of natural numbers or the finite set from 1 to n. Let's also recall the following definition, which was given at the previous lecture. By definition, the I Fourier coefficient of a vector little x in H is the following number, the inner product of x and EI. And now we give the following definition. We define the Fourier series of x with respect to our family EI is the following formal expression. The sum over I Ci EI. So at this point, I'd like to stress that this is just a formal expression. That is, I don't claim that this series always converges. And in fact, we will see fairly soon that if H is complete, then this series indeed converges to some element of H. But at this point, this is just a formal expression. We have the following simple proposition. This is proposition 1. Which describes some basic properties of Fourier series. First of all, let x be an element in H, and let's suppose that x can be written in the following form. So this is either a finite sum or the sum of a convergent series, depending on whether or not I is finite or infinite. Then I claim that AI is nothing but the ith Fourier coefficient. So this simple proposition is sometimes called the uniqueness of the Fourier series. And part 2, suppose now we have two elements, x and y, and H, and suppose that x can be decomposed in the following way. Ci ei, and y can be decomposed as follows. Then I claim that the inner product of x and y can be calculated by the following formula. Ci di complex conjugate. In particular, in the special case where y equals x, we get the so-called Parseval's identity. In particular, the norm of x squared is equal to the following sum. So this is just a special case of the previous formula, which corresponds to the situation where y equals x. This is the so-called Parseval's identity. By the way, let's recall from the previous lecture that for an arbitrary x, we have an inequality. That is, the right-hand side here, the sum, is less than or equal to the norm of x squared. But if we assume that x is exactly the sum of its Fourier series, then we have an equality here. Well, the proof is very easy. In case 1, we just calculate explicitly the Fourier coefficients. So by assumption x is the following sum. We can now write this sum in the following way. Well, this is obviously true if I is finite, just by the algebraic properties of the inner product. And if I is infinite, if it is a set of natural numbers, then this follows from the continuity of the inner product. Okay, but our family is EI is orthonormal, so only one summand survives, namely the case where I equals j, and eventually we get just a j. And that's it. So this shows that aj is just the Fourier coefficient. This proves part 1. And similarly, we'll prove part 2. Namely, we substitute explicit decompositions of x and y here. Ci ei dj ej. And again, using the algebraic properties of the inner product and the continuity of the inner product, we get the following double sum over I and j, Ci dj bar, by the inner product of ei and ej. And again, since our family is orthonormal, only those summands survive where I equals j. And eventually we come to the following expression. And that's it. Okay, so now our next goal is to construct a sufficiently large orthonormal family in our inner product space. What do I mean by sufficiently large? Well, in fact, there are at least 3 possible answers to this question. So we give the following definition. We say that our family EI, so as before, EI is assumed to be an at most countable orthonormal family, and we say that this family is an orthonormal basis. An orthonormal basis if each element x in our space has the following form. where AI are just coefficients, complex numbers. And we already know from proposition 1 that if such decomposition exists, then actually EI are nothing but the Fourier coefficients. Actually, we have the following formula. So briefly, EI is an orthonormal basis if each vector in H is the sum of its own Fourier series. By the way, I'd like to stress that an orthonormal basis of an inner product space is not necessarily a basis in the algebraic sense. Of course, if I is finite, then this is true. But if I is infinite, if this is a set of natural numbers, then this is not a finite linear combination. So in general, an orthonormal basis is not an algebraic basis of H. So this is condition 1 on EI. Now condition 2, we say that EI is total. EI is total if the linear span, the closure of the linear span of this family is the whole of H. This equals H. And finally, we say that EI is maximal if it is maximal as an orthonormal set. That is, it is not, EI is not properly contained in a larger orthonormal family. By the way, let's observe that briefly this condition can be written in the following form. The orthogonal complement of our set EI is 0. This is equivalent to the above maximality condition. Ну, если хотите, я вот так вот более напишу корректно. Ну, то есть он как множество, понимаете, формально это семейство. В семействе немножко разные вещи, но если мы рассмотрим его как множество, всех этих самых и так соберем их всех в одно множество, то он просто будет максимально в классе всех ортонормированных множеств.
То есть получается, что яиты не обязаны быть... Сейчас, если все яиты друг другу ортогональны, а у нас формы невыраженные, положительно определенные, то как-то мне казалось, что не может так быть, чтобы у нас было два базиса, чтобы через оба этих базиса выражалось, и при этом один был как множество больше элементов.
Так здесь же мы не предполагаем, что это базис. Это три разных условия. Здесь яита — это ортонормированное семейство. Какое это ортонормированное семейство? Вот. И мы называем его максимальным, если оно максимально вот в этом смысле. То есть просто его нельзя увеличить.
Что это максимально ортонормированное семейство, но не максимально ортонормированный базис.
Нет, это три разных условия. Это три разных условия. So formally we have, at this point, we have three different conditions. In some sense, each of them means that our family is large. But formally, they are different. Formally, they are different. And by the way, in the old Russian language literature, maximal orthonormal families are sometimes called complete, and total orthonormal families are called closed. But in my view, this is not a very good terminology, because complete and closed are a bit overloaded notions. We have complete metric spaces and closed sets. This terminology is gradually going out of use. So I prefer to use the words total and maximal, which are, in a sense, self-explanatory. So maximal means maximal in the usual sense of the word. Okay, now let's let's now look at relations between these three properties. So we have the following theorem. So consider the following properties. Of our family EI. Property 1, EI is an orthonormal basis. Property 2, EI is total. And property 3, EI is maximal. I claim that 1 and 2 are always equivalent, and they imply 3. And if moreover we assume that H is a Hilbert space, if H is a Hilbert space, then all three conditions are equivalent. Okay, so if we look at the definition here, well, it's more or less clear that 1 implies 2. Because if we have this decomposition, if I is infinite, this is sum of series, then of course X is approximated by a finite sum of the series, and we have condition 2. And of course, if I is finite, then everything is clear. 1 implies 2. So it's clear that 1 implies 2. Let's now show that 2 implies 1. This is a bit harder. 2 implies 1. So we suppose that EI is total. This means that the linear span is dense. And for each k in I, let hk denote the linear span of finitely many elements in our family from E1 to Ek. And let little x be an element in our space. So by assumption 2, for each positive epsilon, we can find an index k0 in I such that the distance between x and hk is less than epsilon. hk0 is less than epsilon. This means exactly that x can be approximated by a finite linear combination of our elements. Okay, now if we take any index bigger than k0, for each k greater than or equal to k0, we have the same inequality. The distance between x and hk is less than epsilon, just because hk contains hk0. But in the previous lecture, we have already calculated this distance. This distance is the distance between x and the orthogonal projection of x onto hk. And the orthogonal projection is given by the following explicit formula, sum ci ei, where the sum is taken from 1 to k. This equality was proved at the previous lecture. Actually, we proved that this sum is precisely the orthogonal projection of x onto hk, and we already know that the orthogonal projection is the nearest point. So this distance is equal to this distance. Okay, so now we see that for each epsilon there is a number k0, such that for whenever k is greater than or equal to k0, we have this estimate. But this means exactly that X is the following sum. So we see that EI is an orthonormal basis in H. Okay, now we now show that 2 implies 3. This is very easy. So if EI is total, we take the set of all elements in our orthonormal family and take the orthogonal complement. So by the basic properties of orthogonal complements, this is equal to the orthogonal complement of the closure of the linear span of the same set. But by assumption, EI is total, so the closure of this linear span is H, and the orthogonal complement of H is 0. So this orthogonal complement is trivial, which means that EI is maximal. And finally, let's suppose that H is a Hilbert space. And let's show that 3 implies 2. So we assume that EI is maximal. We want to show that it is total. Well, let H0 denote the closure of this linear span. This is a closed vector subspace of H. And H is a Hilbert space. And so we have the orthogonal complement theorem. So by the orthogonal complement theorem, we have the following decomposition. But EI is maximal by assumption, so this orthogonal complement is 0. And we conclude that H equals H0. In other words, EI is total. And this completes the proof. So I'd like to stress once again that here in the implication 3 implies 2, it's essential that H is complete, that is, it's a Hilbert space. And the completeness is hidden in this formula. So if H is not complete, then we cannot use the orthogonal complement theorem, and everything fails. Ну, давайте посмотрим. Значит, йиты у нас максимальное, да? Это означает, что ортогональное дополнение ко всем йитам нолик. Но, значит, ортогональное дополнение к этому тоже нолик. Ну да, ортогональное дополнение к множеству, и ортогональное дополнение к замыканию линейной оболочки, они просто одинаковые.
Получается, что 0 ортогональное, но...
Да. Угу. Вот это, то, что это нолик, это как раз и означает в сущности, что наше семейство максимально. Okay, now our next goal is to show that if H is separable, then we can always construct an at most countable orthonormal basis in H. And the key tool for this result is the following lemma. Suppose that H is an inner product space. And suppose that xi is an at most countable, linearly independent family in H. And as before, we assume that I is either a set of natural numbers or a finite set from 1 to n. And for each k in I, let hk denote the linear span of elements x1 to xk. I claim that there exists an orthonormal family, EI, of the same cardinality, that is at most countable, in H, such that for each k in I, the linear span of the elements E1 to Ek equals HK. Well, in fact, this is a classical algebraic result. The proof is well known. This is the Gram-Schmidt Orthogonalization. First of all, we define E1 as follows. We just normalize the vector x1. And now assume that we have already constructed the vectors E1 to, say, En minus 1. So assume that E1 to En minus 1 are already constructed. And we construct En as follows. First of all, we define a vector En prime by the following formula: xn minus the following sum from 1 to n minus 1. Here we take the Fourier coefficient of xn with respect to our family EI and multiply by EI. So what can we say about this vector? Well, we know that this sum is nothing but the orthogonal projection of xn onto hk minus 1. This is the orthogonal projection of xn onto hn minus 1. And by the definition of the orthogonal projection, this difference is orthogonal to hn minus 1. En prime is orthogonal to hn minus 1. And also it is non-zero. It is non-zero because our family is linearly independent. The family is linearly independent, and so xn doesn't belong to hn minus 1. So this difference is non-zero. And to complete the proof, we just let En be the normalization of En prime. And this is exactly what we're looking for, because by construction, our family is still orthonormal. By construction, E1 to N is an orthonormal family, and the linear span of E1 to En is Hn, just by construction. And this completes the proof. And now we are ready to prove the following theorem. If H is a separable inner product space, then there is an orthonormal basis in H.
Inner product space — это синоним для Гильбертова пространства или есть разница?
Синоним чего?
Гильбертова.
Нет, Гильбертов — это полное. Пространство с скалярным произведением — это просто векторное пространство, на которое введено скалярное произведение. Мы больше ничего не требуем. А вот если оно еще и полное, то говорят, что оно Гильбертово. Пространство с скалярным произведением еще иногда называют предгильбертовым, иногда называют эрмитовым, иногда называют унитарным, иногда называют комплексно-евклидовым. Это все синонимы. Вот. А вот Гильбертово — это уже такой стандартный термин, это пространство с скалярным произведением, которое еще вдобавок еще и полно. И вот видите, где-то мы тут не пользуемся полнотой в каких-то местах, да? Например, когда вот предыдущий теорем доказывали. А в каких местах пользуемся? Вот когда мы вот эту импликацию доказывали, нам тут полнота понадобилась.
То есть Гильбертово — это Банахово с внутренним произведением?
Можно и так сказать, да, это Банахово пространство, норма которого происходит из какого-то скалярного произведения. Okay, let's now prove this result. Well, since it is separable, we can always find a total linearly independent family. H is separable. This implies that there exists an at most countable linearly independent family Xi in H, which is total, that is such that the closure of the linear span of this family equals H. Well, this is almost immediate from the separability assumption. To construct such a family, we first of all take a countable dense subset of H, and then throw away those elements which are linear combinations of the previous elements. And as a result, we get an at most countable linearly independent total family. So we take this family, Xi, and we apply the orthogonalization process. And we come to an orthonormal family, EI, and the previous lemma implies actually this condition. This condition here obviously implies that the linear span of all elements EI is equal to the linear span of all elements Xi, which is dense in H. So EI is total, or equivalently, it is an orthonormal basis. And that's it. Okay, let's now look at some concrete examples of orthonormal basis. Example 1. Suppose that H is just Cn with a standard inner product. And let EI denote the following vector in H. So here 1 is in the ith position and 0 is elsewhere. So it's clear that E1 to En is an orthonormal basis. It is obviously orthonormal, and it's even an algebraic basis of H. So each element in H is a finite linear combination. Example 2. Suppose now that H is the little L2 space of square summable sequences. And similarly, we denote by EI the following element. Now, it's an infinite sequence in our space with 1 in the ith slot and 0 elsewhere. Well, it's easy to see that EI, now it is countable, EI is an orthonormal basis. In L2. It is obviously orthonormal. And why is it an orthonormal basis? Well, actually, we can easily verify each of these three conditions. For example, why is it maximal? Well, it is maximal because if some element is orthogonal to each of them, say x1, x2, x3, and so on, then when we calculate the inner products, we see that all the coordinates of this vector x are 0. So it is maximal. And it is also very easy to see that it is total and that it is an orthonormal basis in the sense of condition 1. Okay, but this is an orthonormal basis, but it is not an algebraic basis. It is not an algebraic basis because the linear span of all these elements is strictly smaller than L2. The linear span consists of all finite sequences. That is, of those sequences which are eventually 0. Of course, it is strictly smaller than L2. Example 3. You would take the trigonometric system, which was discussed at the previous lecture. Then it turns out that the trigonometric system is an orthonormal basis in the L2 space. On the interval minus pi pi, or equivalently in the L2 space on the circle. This is not entirely obvious, but this is a classical fact, and I hope that this was proved in your calculus course. This is quite standard. In fact, this is one of the most classical orthonormal bases. By the way, at the previous lecture, we have also discussed the Erdemacher system, which is an orthonormal family in the big L2 space on the interval 0, 1. So the Erdemacher system is not an orthonormal basis. It's quite easy to construct a function which is orthogonal to all elements of the Erdemacher system. But on the other hand, if we add finite pointwise products of Rademacher functions, what we get is the so-called Walsh system. And there is a theorem which says that the Walsh system is an orthonormal basis in L2, 0, 1. Example 4 is also quite classical. So let H be the L2 space on the real line, equipped with the Lebesgue measure. And let's denote by xn the following function on the real line, given by the following formula. So for each non-negative integer n, it's easy to see that this function is in L2. So we can form this function for each non-negative integer n. They are clearly linearly independent. So we can apply the orthogonalization process. And we get a new family denoted by Hn. This is an orthonormal family. And these functions Hn are called the Hermite functions.
По Gram-Schmidt ортогонализуем каждое следующее после предыдущего.
Да, совершенно верно. То есть применяем вот то, что написано в этой лемме, буквально, и получаем эти Hn. So Hn are called the Hermite functions. And it turns out, this is an exercise for you, which is not very easy, but still reasonable. Hn is an orthonormal basis. In the L2 space on the real line. Hint is to use the Fourier transform. Okay, let's now prove an important classification theorem for separable Hilbert spaces. Classification of separable Hilbert spaces. So case 1, suppose that H is an infinite dimensional separable Hilbert space. We choose an orthonormal basis, EI, an orthonormal basis in H, which is strictly countable because H is assumed to be infinite dimensional. And we consider the following map, that's denoted by U, from H to L2, which acts by the following formula. It takes each vector little x to the sequence of its Fourier coefficients. And I claim that this map is a unitary isomorphism. So we see that each infinite dimensional separable Hilbert space is unitarily isomorphic to little L2. And case 2 is the case where H is finite dimensional. Suppose that H is a finite dimensional Hilbert space. So in this case, we can choose a finite orthonormal basis. In H. And in this case, the following map, U, which acts from H to Cn, and again it takes each element x to the family of its Fourier coefficients, is a unitary isomorphism. Is a unitary isomorphism. So we see that the classification of separable Hilbert spaces is very simple. We have finite dimensional Hilbert spaces, Cn, and we have little L2. And that's it. So there are no other separable Hilbert spaces up to unitary isomorphism.
Можете напомнить, что такое сепарабельное?
Сепарабельное означает, что есть счетное плотное подмножество. То есть сепарабельность понимается просто в топологическом смысле. Okay, let's now prove part 1. So first of all, we know that this sequence, the sequence of Fourier coefficients, is indeed square summable. This follows from Bessel's inequality. Bessel's inequality means exactly that this sequence is square summable, and so U is indeed a map from H to L2. Moreover, proposition 1 from today's lecture implies that U preserves the inner product. The inner product of Ux and Uy equals the inner product of X and Y. This is part 2 of proposition 1. So the inner product of X and Y, if Ci are the Fourier coefficients of X and Di are the Fourier coefficients of Y, then the inner product of X and Y equals the corresponding sum, Ci multiplied by Di complex conjugate. That is the inner product of Ux and Uy in L2. So to show that U is a unitary isomorphism, we now have to show that U is surjective. So ну да. Тут сказано, что вот эта формула, вот эта часть левая, смотрите, ну давайте я вам напишу. So if X is given by the following formula and Y is given by the following formula. So U of X is nothing but the sequence Ci, and U of Y is the sequence Di. So U of X and the inner product of U of X and U of Y is the inner product of these two sequences in the little L2 space. So this is the following sum, and this is nothing but the inner product of X and Y by proposition 1. Okay, so what is a unitary isomorphism? A unitary isomorphism is a bijective linear map which satisfies this condition. But this condition already implies that U is isometric, so it is injective, the kernel is trivial, and to show that it is a unitary isomorphism, it suffices to show that U is surjective. Now we have to show that U is surjective. To show that U is surjective, we do the following. We consider the space C00 of finite sequences. That is, this is the space of those sequences of complex numbers which are eventually 0. In other words, xi equals 0 for all but finitely many I. So what can we say about C00? First of all, C00 is dense in L2. If I have a square summable sequence, we just can fix a natural number n and throw away all elements xn plus 1, xn plus 2, so let them equal to 0. We get a finite sequence which is very close to the original sequence in L2. So C00 is dense in L2. Second, it's clear from the construction that C00 is contained in the image of our operator U. Because, finite linear combinations of our orthonormal basis go exactly to finite sequences. So C00 is contained in the image of U. And finally, we observe that the image of U is closed in L2. Why is it closed? It is closed because it is isometrically isomorphic to H. It is isometrically isomorphic to H, and H is complete. So this implies that the image of U is also complete, but a complete metric space is always closed in any bigger metric space. So these facts together imply that the image of U is all of L2. It is conditions A and B imply that the image is dense, but it is closed, so it is all of L2. And so U is surjective. And since it preserves the inner product, we conclude that U is a unitary isomorphism. Now this completes the proof of part 1. Now the proof of part 2 is similar, and in fact it is even easier than the proof of part 1. So essentially the same argument, which doesn't involve C00, shows that in this case, in the case of a finite dimensional Hilbert space, this map U is a unitary isomorphism. And here's an important example. So if we take the big L2 space over the real line, we see that there is a unitary isomorphism of L2 over the real line onto the little L2 space. And here it will be convenient to consider the little L2 space over the non-negative integers, including 0. So there is a unitary isomorphism which takes the nth Hermite function to the nth vector of the standard basis in the little L2 space. So as before, En is the following element. This is just a special case of this theorem. And by the way, this example has a deep physical meaning because it gives us an equivalence between Heisenberg's picture of quantum mechanics, which sits here, and Schrödinger's wave quantum mechanics, which sits here. But this is quite a long story. You can find details in any book on mathematical methods of quantum mechanics. Okay. A useful corollary of our classification theorem is the following result, which is usually referred to as the Rees-Fisher theorem. Corollary. Suppose that H is a Hilbert space. And suppose that Fi is a countable orthonormal family in H. Then I claim that for each square summable sequence Ci, that is a sequence Ci in L2, the following series, some Ci Fi, converges in H. To prove this result, we take the closure of the linear span of this orthonormal family. So let H0 denote the closure of the linear span. А ваш у нас только одна сходимость. Там H это какое-то гильбертово пространство, там есть норма. Просто сходится по норме. Это же не какие-то функции, это элементы абстрактного гильбертового пространства, поэтому там не так уж много вариантов сходимости. Ну, просто сходится как последовательность частичных сумм сходится по норме. So we denote by H0 the closure of the linear span of all these elements. So what can we say about H0? H0 is an infinite dimensional separable Hilbert space. It is separable because we have countably many elements here, and it is a Hilbert space because it is closed in H, and H is a Hilbert space. So it is an infinite dimensional separable Hilbert space, and Fi is an orthonormal basis of H0. So the above theorem implies that there exists a unitary isomorphism. U from H0 to the level 2 space given by the following formula. So in particular, we see that U takes Fi to Ei, where Ei is the ith standard basic vector of L2. Замыкание линейной оболочки. А мы это не знаем. У нас ведь Fi это ортонормированное семейство, не обязательно базис. Не обязательно базис, просто какое-то ортонормированное семейство. Может быть, не базис.
То есть мы даже не знаем, что он такая?
Нет, мы это не предполагаем. Просто какое-то ортонормированное семейство. Просто какое-то ортонормированное семейство, не обязательно базис. Вот, поэтому H0 может быть и меньше, чем H. Но зато H0 уже вошло, это уже будет базис ортонормированный. Okay, so this formula for U implies that U takes Fi to Ei, where Ei is given by this formula. And clearly, if we consider the following series, CI, then it converges to C in L2. Just by the definition of the little L2 norm. And we apply U. So U is in unitary isomorphism. It takes convergent series to convergent series. Or more exactly, we apply U inverse. We apply the inverse map. And we conclude that the respective series in H, the series CI, converges in H0, and moreover it converges in H. And that's it. Okay, by the way, our approach to the Riesz-Fischer theorem is not entirely standard. Quite often, one usually first proves the Riesz-Fischer theorem and then deduces from it the classification theorem. This is also rather easy, but it requires some extra work. So in my view, our approach is a bit shorter. So first we prove the classification theorem and then deduce the Riesz-Fischer theorem as a corollary. Okay, so that's all I wanted to tell you about structure theory of Hilbert spaces. Our next goal is to discuss dual spaces of normed spaces. So suppose that we have a normed space X, a normed space, over the real or complex numbers. So as before, I denote by K the field of real numbers or the field of complex numbers. And by definition, the dual of X, or more exactly the topological dual of X is the following space, which is denoted by X star, and this is the space of all bounded linear operators from X to the base field K. So I add the word topological here in order to distinguish between the topological dual and the algebraic dual of X, which consists of all linear functionals, and which is also usually denoted by X star. But in functional analysis, we usually denote by X star the topological dual, and this is okay. So this doesn't lead to any problem. Well, by the way, let's observe that the dual space X star is always a Banach space. Well, indeed, some time ago we proved that if X is a normed space and Y is a Banach space, then B of xy is a Banach space. And here Y is just the base field, which is complete. So X star is a Banach space. Well, in fact, a substantial part of Banach space theory and of operator theory between Banach spaces is based on very nice interplay between spaces and their duals. Before we prove some general results about dual spaces, let's look at some examples. So our goal will be to describe the dual, to explicitly describe the duals of some classical Banach spaces. And we start with the case of a Hilbert space. So let's look at the following example. Suppose that H is an inner product space, and suppose that little y is an element in H. Okay,